All right, today's lecture is going to be looking at how we can utilize the ideal gas law in stoichiometry problems. Okay? Now, again, whenever we have a stoichiometry problem, somewhere in there we are going to have a mole to mole step. We're going to utilize the mole ratio, which means we must have a balanced equation. The balanced reaction is important because it will allow us to convert from moles of one substance to moles of something else. Now, when we do this, some point, now typically in solids, if you remember back to Unit 1, with solids, we typically were looking at stoichiometry in which we were from grams of A to grams of B. We were doing mass-to-mass problems. In the second unit, we are looking at solutions. And in solutions, we are looking at going from molarity of A to molarity of B and utilizing the molarity equation. Now with gases, the most common thing that you might measure with a gas is its volume. And that's where the ideal gas law comes in handy. The ideal gas law allows us to convert from the moles of a gas to the volume of the gas. So if I'm able to measure the volume of gas generated by a chemical equation, I can easily convert it to moles. If I take the pressure, volume, and temperature of the gas, I can easily convert that into the number of moles. Okay? Now, if we are at STP, if in the problem they tell us we're at STP, and again, STP would be 1 atmosphere of pressure and 273 degrees Kelvin. I should say 273 Kelvin, there's no degrees. When we are under those conditions, we can utilize what's called molar volume. It's a conversion factor that allows me to convert from moles, N, to volume, V. And I can just simply utilize 22.4, just like I use 6.02 times 10 to the 23rd number of atoms to moles, okay? So I can use in one of the conversion factors this number to convert from liters to moles. What happens when we're not at STP? If we're not at STP, then we have to use the ideal gas law. We have to use the ideal gas law to convert between volume and moles so that I get the variable that I want and then continue on with the stoichiometry. If we're at STP, we can still use the ideal gas law. We can plug in the pressure and temperature, which is 1 atmosphere and 273 K. We'll still get the same answer as if we use 22.4. So when in doubt, if you're not sure, use the ideal gas law to convert from the volume of a gas to its moles, or vice versa, the moles to its volume. All right, problem 1. What mass in grams of potassium chlorate must be used to produce 1.5 liters of oxygen measured at 18 degrees Celsius and 0.95 atmospheres? All right, again, we have been given a quantity, a unit of measurement. In this case, for a gas, it's often volume. We've been given the volume of a gas, but we want to know the mass of an ionic compound, which is a solid. Potassium chlorate is a solid. We need to figure out how many grams comes from this volume. So in our problem, we are going from liters of oxygen to grams of potassium chlorate. It's a stoichiometry problem because somewhere in this problem, we're going to have to convert from oxygen to potassium chlorate. So the first step in doing this is we know somewhere we're going to have to do the mole-to-mole ratio problem. In order to do that, we're going to need the balanced equation. So pause my lecture right now and quickly get the balanced equation for this chemical reaction. All right, potassium chlorate decomposes into potassium chloride and oxygen gas. Metal chlorates produce a metal chloride and oxygen gas. So they did tell us that oxygen was produced, so that should have told us that the potassium chlorate was the reactant. Okay? The coefficients are 2, 2, and 3 for the balanced equation. All right, you'll notice that the first thing, we want to figure out the mass of the solid is my question mark, that's what I'm trying to solve. We know the volume of the gas, we know the temperature and the pressure. First of all, are we at STP? Are these STP conditions? The answer is no. So I've got the volume of a gas, I've got the temperature of the gas, and I've got the pressure of the gas. This is screaming that I need to use the ideal gas law. Okay? So if I look at PV equals nRT, if I have the pressure, the volume, and the temperature, and R is a constant I can always look up, The variable that I don't know is the moles. I can convert the volume of oxygen into the moles because my framework needs to go from liters of oxygen into moles of oxygen. And then once I know the moles of oxygen, I can go to the moles of the potassium chlorate. That is what makes it stoichiometry. And then I can go to the grams of potassium chlorate. I'm doing a liter to mass problem. All right, so if I rearrange this equation for n equals PV divided by RT. So 0.95 atmospheres. The volume is 1.5 liters. Again, the volume must be in liters when we use the ideal gas law. The gas constant to use is we are in atmospheres. So whenever we are in atmospheres, we're going to use 0.0821 for the R constant. And then the temperature must be in Kelvin. So 18 plus 273 gives us 291 Kelvin. Okay, going ahead and doing the mathematics of this, 0.0596 moles of oxygen. Okay? All right, so now I need to do the stoichiometry. To go from moles of oxygen to moles of potassium chlorate, we need to use the mole ratio. Whatever unit we have becomes the next unit on the bottom. Our mole ratio here is 2 to 3. And then we need to add up the molar mass of potassium chlorate, which is 122.55 grams. All right, go ahead and multiply across, and we get our final answer. I'm going to round it to 3 sig figs, 4.87 grams. So we would need 4.87 grams of potassium chlorate to produce 1.5 liters of oxygen gas under those conditions. Okay? Go ahead now, pause the lecture, and try to do problem 2, utilizing these same types of steps, maybe in reverse order potentially. Okay? All right, the balanced equation is the combustion of butane. So again, butane, in our combustion reaction, we need oxygen as a reactant, produce carbon dioxide and water in all combustion reactions, and we get the following ratio: 2, 13, 8, and 10. Now in this problem, we have been given 1 gram of butane. And we are asked to figure out the volume of oxygen. So we're going from grams of butane and converting to volume of oxygen. Again, we are not at STP. Since we are not at STP, and STP in millimeters of mercury would be 760. So 725 is not at STP. And the temperature isn't at 273 Kelvin. So therefore, what we are going to have to do is, starting with mass of butane, what's the first thing we can always convert grams into? Hopefully you're screaming at me, moles. And 1 mole of butane has a mass of 58.14 grams. Next step. Once I know the moles of one thing, I can always find the moles of something else. In this case, the oxygen. So again, whatever unit is on top becomes the next thing on the bottom. Now, if we were at STP, I could keep on doing this problem and do a third step where I could utilize the 22.4 liters per mole. But since we're not at STP, I have to stop here. Okay? So going ahead and doing the math, I end up getting 0.111 moles of oxygen. So now I know the moles of the oxygen. I also know the pressure of the oxygen. And I also know the temperature of the oxygen because that was given to us in the problem. 725 millimeters of mercury, 21 degrees Celsius. So I know the moles is N. I know the N, P, and T. I always know R. So in order to find the volume, again, because we're not STP, I can use the ideal gas law. So PV equals nRT. Solving for the volume, I'll divide by P. And so now it's the mole quantity times the R. Now we're in millimeters of mercury, so the R that I'm going to use must be the millimeters of mercury guy, which is the 62.36. The temperature must be in Kelvin, so we're going to add 273 to that, and we get 294 Kelvin, divided by the pressure of 725 millimeters of mercury. Moles times R and temperature divided by pressure gives me the volume in liters. Doing the math in the calculator, we get 2.83 liters of oxygen. So problem 1, we are going from the volume of a gas to the mass. Problem 2, we're doing the exact opposite, taking the mass of a substance and going to the volume of it. So these, again, like I've always said before, if you know how to do the problem one way, you've got to be able to do the problem backwards. Okay, number 3 is looking at when we have multiple gases in a chemical reaction. If I know the volume of one gas, how can I figure out the volume of another substance that's also in the gaseous state? And the key here is right here at the end of the question. If we are at the same temperature and pressure, this problem becomes very simple. Now, if we were not, if the temperature and pressure conditions were changing, we would have to use the ideal gas law to convert the volume of gas A to its mole quantity under the first set of conditions. Then we could use the mole ratio to convert the mole B, and then to go to the volume of B, we would have to use the ideal gas law again, but under the new pressure, temperature, and volume conditions. So this problem would involve 3 steps. But if the temperature and pressure are constant, we can treat a volume of a gas to a volume of a gas. We can treat that just like moles to moles. And a mole to mole problem is 1 step. So if the temperature and pressure are constant, I don't need to worry about step 1 and step 3. All I need is 1 step. I can treat a volume ratio just like a mole quantity because of something called molar volume in Avogadro's law, which states that there's a direct relationship between the moles of gas and the volume of the gas. If I double the moles, I double the volume. And so because this is a direct relationship, I can do this problem in 1 step. Okay? So if the pressure and temperature are constant and I know the volume of one gas, I can figure out the volume of any of the other gases by doing a liter to liter problem. And the only numbers that I need are the coefficients because we treat this just like a mole ratio problem. And in the balanced equation, there are 2 moles of ammonia to every 3 moles of hydrogen. So if I take 12 liters times 3 divided by 2, we get 18.0 liters of hydrogen. Okay, if we were to do this problem at STP, we would end up doing a 3-step problem. We'd end up getting the same exact answer, which gives us validation and proof. When we have a volume-to-volume problem, as long as the temperature and pressure are constant throughout the reaction, the volume of a gas is directly related to the number of moles of the gas. So we can do this in 1 step. All right, so that's how we're able to utilize stoichiometry with gases and using the ideal gas law. Now it's just a matter of you doing enough practice problems that you get really proficient at it, okay? There are some example problems. I think the problems that I have are only in mastering. There are some problems which are conceptual problems, and then there's about 4 or 5 mathematical problems like the ones I had here for problems 1 and 2. To go ahead and do those and try those in mastering, and then provide those answers and see how well you do on them to get practice. Next week we'll have a quiz on gas stoichiometry.